let's move here. So last time, probability of A intersection B is equal to, well, sorry, I need to, the probability of A union B, I need to prove that it's equal to the probability of A plus the probability of B if A intersection B is equal to the empty set. Now, I can use the third axiom. The third axiom tells me that if I have a countable sequence, so infinitely many events, sets, such that they are pairwise disjoint, you can read it there, then the probability of the union is the sum of the probabilities, okay? So what we did was to choose A1 equal to A, A2 equal to B, A3 equal to A4 equal blah, 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 equal to empty set. Anything after 3 is equal to the empty set. Okay? Is our strategy. Now, what we have is that if you take the union of the AI, I going from 1 to infinity, this is exactly equal to A union B, union empty set, union empty set, no contribution there. Okay? So there is no contribution at all from the empty set. It's empty. You add nothing. Literally nothing. Are we good? It's clear? Then, and also, any choice of pairs in this sequence, either you choose the original two and they have empty intersection, or you choose an empty set. Anything you intersect with an empty set is empty, because intersection means belong to both. The empty set has nothing there, so that's it. So what I can conclude is that the probability of the union of the AI, which is equal to the probability of A union B in this particular case, is equal to the probability of A plus probability of B plus the sum from I going from 3 to infinity of probability of the empty set. The same set. You're summing it infinitely often. Now, let's reason by contradiction. I know that the probability of the empty set is 0. It's common knowledge. But here we do not use any intuition, right? Here we want just to use the first 3 axioms there to conclude this. How do I reason? How do I prove that the probability of the empty set is 0? Suppose it is not. Suppose, by contradiction, so we reason by contradiction. Suppose that the probability of the empty set is not 0. So, being a probability, the first axiom tells you that if it is not 0, it should be positive. Right? Any number that you have in mind. If you sum the same number infinitely many times, and this number is strictly positive, what is this? It's infinity, so greater than 1. And what's the issue here?
The subset of the superset is now has probability greater than 1.
Yeah, so actually I still have to use something here. That's tricky. So if there is a third step, unfortunately. If probability of phi is larger than 0, then probability of A union B would be equal to infinity. Are we good? Which is, of course, nonsense. But again, what does it contradict here? Why? How can I infer that?
Because, for example, sets that we are summing together is a subset of the entire superset.
Yes, but I need still to prove that if, let me use, if C is a subset of, I should have started with that, is what I did past years. That's the whole point. Now I find myself in a bad situation, so I need to use something else. I still didn't prove that if C is a subset of D, the probability of C is less or equal to the probability of D. I took a different route. I took a different track. So I need to use something else. I use your suggestion of the epsilon, so you have to help me with this. How do I prove this? But it's practically the same. I need, where is the eraser? Oh. It's nonsense. This is not. So I delete this. I don't want to confuse you. We go back here. But how can I prove that? I want a complete proof now. And we have to do it quickly. So, how can I do it? First of all, I can do this in a different way, like this. So you're right. Let me do it here. Start with the probability. Assume that the probability of the empty set is larger than 0. Then the probability of omega union empty set, union empty set, union empty set. If you want, an infinite amount of empty sets. So the starting point was wrong. Look at this. Now, these are pairwise disjoint, the same as before. This is the probability of omega plus some I going from 2 to infinity of probability of empty set, which does not depend on I, of course. Now, if the probability of the empty set is positive, this would be infinity again. But this would contradict that this is equal to 1. Probability is equal to 1. This would contradict the fact that this should be equal to 1, axiom 2. Contradiction. Okay? So the starting point was wrong, or not useful. Didn't give us information. Now we know that the probability of the empty set is 0. We got a contradiction. And we can definitely say, okay, this is nonsense. This goes away. And this is the happy ending we were looking for. The good news, okay? That we knew from the first unit in probability, in high school most probably, or some of you. I have the impression I'm boring you. Sorry for that, but we will see something more interesting and challenging fairly soon. Okay, let's start to see the implication of all this. It's nice, but I want to see a few concrete things here. Is this clear? Can I delete this part? Any question about it? Because it takes time to dry this thing. So these I will delete. The reasoning by contradiction is clear. And these I delete. cannot be used now. We use this. Perfect. So let's start with the first implication. A and A complement. How do you relate them? What's the relation between the two?
A complement is everything that's not a name.
Yeah, so by definition, what is this? The empty set. So it's empty. Because one has the object that do not belong to the other. So it's empty by the very definition of this guy. What is A union A complement? They exhaust the whole thing. Omega. So the probability of A union A complement is equal to 1. Because it's the probability of omega axiom 2, it's 1. On the other hand, this is equal to the probability of A plus the probability of A complement using what we just proved. They have empty intersection. They are disjoint. Good news, the probability of A is equal to, or if you want, probability of A complement is equal to the probability 1 minus the probability of A, and vice versa. So what is the first item in this page? Yesterday, for those of you in MTH 2225, we saw one example where in order to compute a probability, this is practically the only way to approach the problem. Instead of computing the probability of A, which can be very, very difficult, you can compute the probability of A complement that has the same information, and sometimes it's very easy to compute. So one of the two might be extremely difficult to compute directly. With this innocent trick, you can actually reduce or even be able to compute things, which otherwise would be impossible. Questions? Are we good? I expect you also to give me feedback about the pace that I have a tendency, especially when I use the blackboard, to go fast. So don't feel shy, just tell me right away. Good? Good. So the probability of the empty set is equal to 0. We already proved it. Nothing. We had to use it. We need it. So it's done. Now, what we were saying before, if A, so item 2, item 3 of this page, if A is a subset of B, then the probability of A is less or equal to the probability of B. We saw this. How to prove it? Using the previous, what we saw so far. Not only the axioms, but only what we proved so far. Yes? Go ahead.
Is B like a subset considered P? Is this a strict subset or is this a...
Very good question. When I write papers, I like to make it clear that this is, equality is an option. And this is also consistent with that. Here, though, someone else wrote this. And as much as I'm grateful, I like to criticize his work. He will hear me in the recording, but yeah, he should have used that. It's more precise. Any question? How to prove this? Good. I don't need to raise your hand. Just.
I guess if we take A and B excluding A.
Yes.
Two disjoint sets.
Yes. So I need to, in order to apply what I saw so far, I need these joint sets. I need to find a way. And I need to choose these joint sets such a way that the union is something that is useful for this. Now, strategy. Disjoint, two disjoint set will do, with union being what? B. And one of these two sets must be A. So choose A1 equal to A, A2 equal to B minus A. Again, B minus A has a lot in common with A complement, because it's everything that is listed in B but does not belong to A. In this context, this is B, this is A. So B minus A is everything here. When I take the union of the inner ball with the annulus, I get B. Is clear? Then the end of the story here is probability of B is equal to the probability of A union A1 union A2 is equal to the probability of A1 plus probability of A1 A2. Now, all this is not about equality. Let me write a final step here. I'm not sure if people at home can see it. I really hope things work. Instead of A1, I write A. Instead of A2, I write B minus A. Now look at axiom 1. What is telling you? Yes, go ahead. It cannot be negative. So how do you compare these and simply the probability of A? What is larger or equal? This is larger or equal than this because it's the probability of A plus something that cannot be negative. Okay? So what we prove is the probability of B is larger or equal than the probability of A, as advertised. Is it clear? Okay. This is the starting point for that. I want to prove this is very useful, but is an inequality here. The fourth item, you are going to use it a lot. Have you seen it before, right? Yeah, it's well known. Have you proved it other than the picture proof? Have you seen the proof of it before? Okay, it's about time to prove stuff. How to prove it? Give me any clue that pops up your mind. Let me erase this. probability of A union B is the probability of this plus the probability of this minus intersection. How to prove it? Yes, good.
I guess just direct set.
Yeah.
A as one set and B excluding A.
Yes, 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 yes. So let's start with this, and then I need to consider again B minus A, there's this joint. We start with that. So probability of A union B is equal to the probability of A union B minus A. This is the most economic way to write this union, because it's this A and then this B minus A, okay? They are disjoint now, do you agree? So I write here, this is the probability of A plus the probability of B minus A, and this looks like I'm stuck somewhere here. I need to find the probability of B minus A, what is it? So I'll give, I hope you are familiar with Roman numbers. This is 1, and I'll keep it, I'll let it rest, and I need to find a trick to find the probability of B minus A. Yes, yeah.
Do we use the fact that the probability of B minus A is equal to the probability of B intersection A complement? And go from there?
The section A complement is not, but you are there. The complement, I remind you that when you use complement, omega could be huge. So the complement is not what you want, but you want to subtract that intersection from B. So let's start a new equation. And my starting point is the probability of B. How can I decompose B? Notice that the probability of B appears there, so I would be happy if I have something with probability of B. I'm unhappy at this stage because I have this. This is true, but it's not as useful as that one. Good. Stephanie, right?
Yeah. I have a question on probability of B minus A. Isn't that the same when you write the conditional probability?
Yes, I know. That I did not introduce, but I have a plan for it. The conditional probability will be written like this. So hold on that, but it's similar. Yeah, but I do have a kind of approach, you would say. You will not confuse the two. Or if we agree that I can change the notation, I can do this now. Do you prefer this? But you have to go back to your notes there. I can create confusion with the past. So I will stick with this and make it as small as possible. We good? So the probability of B. Well, again, these joint sets, probability of B minus A union A intersection B. Because B, let's zoom on B. This is B. This is A intersection B, and this is B minus A. I just need to add union this intersection to get the whole B. Do you agree? Do you see this picture? This is B, A intersection B, and this is B minus A. They are disjoint, of course. Okay? So this is the probability of A intersection B plus the probability of B minus A. Exactly, just bring this on the other side. Now, this is equality. This is what I don't want. With this, I'm happy. With this, I'm happy. So I put what I'm happy with, I put it on the same side. What I don't like, I just put it separately. So what I have, the probability of B minus A, which I don't like at this stage, is equal to the probability of B minus the probability of A intersection B. Okay? Are we good? So what I do, this equality, I plug here. So instead of this, I can write probability of B minus probability, so plus the probability of B minus the probability of the intersection, which is exactly what was advertised. Good, still have time. Questions? It's clear? How do I prove the next item?
Could you break it up into cases? So if they're disjoint,
I could,
let's break it.
but there is a direct way. And the direct way is exactly the way you suggested in the previous items.
You could replace the left side of the inequality with what we just proved there, and since then the probability of A to B has to be non-negative.
Exactly. So I just use the fact that the probability of A intersection B is non-negative. So the probability of A plus the probability of B is larger or equal to the probability of A plus the probability of B minus the probability of A intersection B. Because what I'm subtracting is non-negative. I'm decreasing the quantity here. I'm subtracting something that is non-negative. It's clear? So what you have here is that the probability of A union B can be written in this way with equality. So must be less or equal than this through this relation. Okay? So, now, why we need this? It's very useful. It's more useful when you have a lot of sets, and I use it a lot actually. It's called the union bound. And of course, it's extremely useful, this inequality, when you cannot compute this probability here. So when you are unable to do that, you just drop it. Of course, you do not have equality. This is still mathematics, so you cannot just drop stuff. What you have to do is to say, okay, I choose to remove this because I cannot compute. My information doesn't allow me to compute this, but then the information that I get through that is this, and it's an exact information. Doesn't give me exactly what is this value, but it's true. Okay? Good. Aha, the last item. Shall I play the video card now? So I'll prove this through a video, but it's just a bunch of stuff here, if you allow me, that are disjoint with each other. Being disjoint, the union being A union B union C, you get it. I want to prove something a bit more than this, actually. Yes, I don't even know if I make this accessible. I need to think about it. But if I do, I'll provide a video of this. Let me take a note. But what was very urgent was us discussing the first items there. Is it clear? Any question? Good. Soon the interesting part will oh no, again, video. I'm not even that good in doing the drawing here. I don't see the point. If I'm not going to ask you this, I don't see the point of having it in the class. Other than simply an exposure for you to this. It's interesting, but if I have to do it for 4 sets, my philosophy is that I want to do it for n sets, or infinitely many, not just something tedious which brings nowhere. And this takes us to the conditional probability, which we start today. Before we start that, any question? Am I going too fast? In that case, you can ask. You have the chance to slow down. Okay? It's very good. Let's agree on the notation, and let's agree what I mean by conditional probability. And let me actually, my use of the blackboard is not optimal by far. Let me just erase this. Let's have an example in mind. I need to define a model. I'm rolling a die, and these are the possible outcomes. Okay. Now, the probabilities, I just write it here. In other words, P of omega is equal to 1/6 for all omega belonging to omega. Okay? I prefer this way. Now, I roll this die, but I do it mysteriously here, secretly. I roll it, and I tell you that the outcome is even. Yeah. You could question, do I trust this guy or not? But suppose that you do. You take the information very, very seriously. What is the probability now that you see 3 as an outcome, if you do believe what I told you? If you believe what I told you, it cannot be 3. 3 is not even. What is the probability? Is 2. So the probability will be 0, right? I roll the die. I do it here. I don't tell you the outcome. I just tell you that it's an even number. So you receive the information. You have to adapt your model to the information. This is essential. Now, this is a silly example. But in finance, you need to adapt in real time almost to the input that you get. All the information can be used instantaneously to get a good deal, right? The faster you adapt, the better it is. So help me to adapt. What do I do? This is the whole thing of conditioning. Conditioning means simply that I use the information that have been given. Now, how do I do it? That's the way to do it. The probability of A given the information. So in the example, this information is 2, 4, 6 in the example. Okay? Don't just focus on that. It's more general. I'm just telling you how to interpret in the example in the back of your mind. The probability of A given, let's actually put something extra here. This is going to be equal to the probability of A. This is a definition, intersection B, divided by the probability of B. Now, of course, you are dividing, is a definition, but it's exactly what you have in mind. By dividing, you want to be sure you don't divide by 0, of course. So the assumption that you put is if probability of B is larger than 0, then this definition makes sense. Good. So that's before I see all those items here, let's work out this example. What is the probability in the example? The probability to observe 2 or 3 given that B, 2, 4, 6, that is an even number. It's equal to the probability of the intersection. What's the intersection of the two sets? So the probability of the intersection is 2, but you're right, it's going to be 1 over 6, the probability. And the denominator is the probability of 2, 4, 6, which of course this probability is 1/2. So you have 1 over 6 divided by 1/2, and of course this is 1/3. Very good? So it actually fits our intuition. If I give you the information that the even number is there, the probability that 2 is the outcome. In this case, I asked you 2 or 3, but 3 has no chance to be there. It's 1/3 because it's just one of the 3 options. Are we good? So read the first item there. If B is a subset of A, yeah, then the probability of A given B is equal to 1. Why? At this stage, the only tool that we have is the definition itself. Questions? Is it clear to everybody? Is equal to, this is the probability of A intersection B, is equal to the probability of A, probability of A given B is equal to the intersection B. This intersection, what is it? B. It's going to be B. Why?
Is a subset of A, then all of B has to be in A?
Yes. So B is a subset of A. Then B intersection A is equal to B. How do I prove it? If omega belongs to B, then omega belongs to A, then omega belongs to A intersection B. And a similar argument. So you prove the inequality considering cases, 2 cases. You get equality. It's clear what I mean here? It's the strategy we used the past days. If that is not clear, look what happens by the picture. This is B, this is A. What's the intersection? B. In any case, this is probability of B divided by the probability of B. Nothing is 0 here, everything is positive, so this is nice 1. We good? Questions? Friday, almost there. If A is a subset of B complement, the probability is 0. What does it mean? Okay, let's go by the example again. The probability of 3 given 2, 4, 6. So in the example again, what's the intersection? So the denominator is 1/2. The probability, what's the intersection here? The empty set, so I get a nice 0. Whenever the intersection is the empty set, I get a nice 0. So let's go back to this. If A, more generally, if A is a subset of B complement, then the probability of A intersection B is the probability of the empty set, so it's 0. So this is more general. We can definitely say that the probability of A given B is equal to 0, because it's the ratio of these divided by the probability of B. It's clear? The last one, helping me with this. This is still a bit boring, I know, but we're there. Next topics will be more rewarding. Actually, I have 3 minutes. Yeah, let's do it. If A is a subset of B, then A intersection B is equal to A for the same reasoning as here. And then we have that the probability of A given B is equal to the probability of A intersection B divided by the probability of B by definition. And now I apply this simple deduction. I don't know how you say. You get this. Okay? That's very boring. What is less boring is this one, and we start with that next week, but not with me. I'll be in a workshop, so Monday and Wednesday someone else will take care of the unit, then I'll come back. So I'll see you next Friday, most probably.